Hello, geometry. Welcome to lesson 11.3 on pyramids and cones, right? So now we're focusing on having only one base, because on the other side we have a point that we come to, the pyramid's point. And then this time your lateral faces are now going to be triangles. Okay? All right, so let's take a look at the notes here. I believe we start off with Cavaliers Principle, right? So same kind of idea here, right? How are the volumes of pyramids and cones with the same base area and height related? Okay, so again, same base area and height. So if you take a look here, right, this is a little approximator, right? So we have here a cylinder, right? This is an oblique cylinder, right? So we have these cardboard discs, right? And we're going to stack them. Each has a slightly smaller radius than the previous disc. So it's getting smaller, smaller. You can stack the discs in different ways, right? So let's take a look at this tool and see how they let you stack them. So I can change the angle at which it's leaning, I think, right? See, I can make it, I can almost make it straight up and down. I can make it leaning to the left, right, leaning in the middle, leaning to the right. Okay. Again, I can increase the number of discs. So I make those radii smaller and smaller. I can change the height, change the radius, right? I can hide things. Okay. So it says the heights of the stacks are the same. So each of those discs is the same. And the area at each level is the same. The total volume of cardboard in each stack is the same. So again, as I change the stack, it doesn't matter. So based off of, and again, if I hide, let me see if I hide the cone. There's the discs. All right. So the idea is that if I hide, I can apply Cavaliers Principle to these cones and pyramids. So again, if at the same level you have the same cross-sectional area. So if you look here, if these purple are the same, if the tan or the orange, if the other same, then the heights are the same as well. These two pyramids will have the same volume. Okay, and again, it's just Cavaliers Principle applied to pyramids. So again, Cavaliers Principle, two figures have the same height and equal area at every cross-section. They have equal volumes. Now, for a pyramid, you're going to see that a pyramid is just 1/3 of a prism. So this is going to be the volume formula for a pyramid, right? And that's because we come to the tip. So the next slide is going to demonstrate that or explain that further. So here's the volume formula for pyramids and cones. Again, it's 1/3 the area of the base times the height. Again, I cannot emphasize enough that you're finding the area of the base, not just taking a dimension of the base, right? That's your 2D. And then your height gives you your third dimension, right? And for a cone, of course, the area of the base is the area formula for a circle. So they have that special formula there. These are on the state reference sheet. Now, the one thing to emphasize, right, is that this H must be the perpendicular height. So if I use this color, notice originally it was a right angle here. That must be perpendicular. We're going to learn something called the slant height, which goes out here. This is called the slant height. I think they call it L, or they call it, S, I don't know, slant height, right? L for slant. But we don't use that, right? We use the height on the inside. So be aware of that as we go through some problems. Okay. All right, so example 2, it says, Kyle's truck can haul 1.75 tons of corn per load. 1 cubic meter of corn weighs 0.8 tons. How many loads will Kyle haul to move this pile of corn? So we're given a conversion factor, right? 1 cubic meter. 1 meter cubed equals 0.8 tons. So we need to see how many tons this pile of corn is. We're going to assume that this pile here is a cone or a conical pile. So the cone's volume is 1/3 pi r squared h. This 4 is the diameter, so my radius is half of that, which is 2. And this is the perpendicular height, so that's what I want. So to find the volume, I take 1/3 pi times 2 squared times 1.5. If I type that in all at once, my volume is roughly 6.28 cubic meters. So now I need to convert that to tons, right? If 1 meter cubed is 0.8 tons, we need to take this number and multiply by 0.8. Right? If you think of it as dimensional analysis, this is 0.8 tons over 1 meter cubed. The meter cubes cancel, and that's why we multiply this. So 6.28 times 0.8 is 5.024 tons. And now, if 1 hall is 1.75 tons, we're going to take the 5.024 and divide by 1.75. And when we do that, we get 2.87. And again, this is an instance where you have to round up. No matter what you got, if it's anything above 2, that means he has to take that third truckload. So he's going to take 3 loads. Okay, and then last but not least on this video, part B. So it says Jason is using the mold to make 12 candles. How many cubic inches of wax does he need? So this is a triangular pyramid, right? So this is our base. The volume is 1/3 the area of the base times the height. It is a right, or it's not a right triangle, but they give us the base and height. So to find the area of that base, we're going to take 1/2 base times height, which is 3 times 4, or 4 times 3. Half of 12 is 6. The height here from the base to the tip is 6, and I'm going to assume that is perpendicular because it's up and down. It's not this angled height. It's not this slant height, right? It's up and down. Excuse me. So volume equals 1/3 times 6 times 6. 1/3 of 36 is 12, and that'd be inches cubed. We need to make 12 candles. Each candle is 12, so we have to take 12 times 12. And 12 times 12 is 144, and that would be cubic inches. That's how much wax we need to make 12 of these triangular pyramid-shaped candles. All right, that was video 1. Video 2 is coming right up.